Okay, so now we're going to prove problem 20C in Burton's number theory book, which states that if the GCD of AB is equal to 1, then the GCD of AC and B is equal to the GCD of C and B. So let's go ahead and start the proof. So we're going to assume the GCD of A and B is equal to 1, and this implies that AX plus BY is equal to 1, where of course X and Y are integers, right? So what we can do, since we have this equation here, we can actually multiply both sides by C times D, because I want AC here, and then I would get the GCD of AC and B if I were to multiply both sides by at least C, right? So let's go ahead and do CD, because that'll come in for this here. So I multiply both sides by CD. AX plus BY is equal to, of course, 1 times CD is CD, where C and D are integers. Okay, so let's go ahead and distribute that. Integers not 0, right? I'll put minus 0, right? Integers not 0. So I'll do A C x d plus b c dy is equal to CD. Now, I have the linear combination for AC and B, right? AC and then XD. X is a integer and D is an integer. So that's AC times an integer plus B times CDY. All these are integers, so their product is an integer. So I have AC times an integer plus B times an integer, which is the GCD of ACB. Now, in order to get the GCD of CB on this side, I have to get plus B times an integer, right? But I can just do that over here. I can add this term again to both sides, and I'll show you what I mean. So this implies that AC times XD plus 2B CDY is equal to CD plus B CDY. Notice I just added B CDY to both sides of this equation, and I got that 2 there. And now what I can do, I can rewrite it like this to fit it in the form that I exactly want. AC times XD plus B times 2CDY is equal to C times D plus B times CDY. So now this is an integer, this is an integer, this is an integer, and this is an integer. So now what I can do is I have this linear combination with AC times an integer plus B times an integer. So this implies that the GCD of AC comma B is equal to, and I have C times an integer plus B times an integer, so I can rewrite this as the GCD of C and B, which is exactly what I wanted. And that's the proof for part C of question 20.